Hi. In this lesson, I want us to look at some of the other factors that have an influence on the deformation of rocks. Let's start by thinking about time. It's an important idea in geology, but the time that stress is applied to a rock can have a significant influence on the strain or the deformation that occurs as a result. Let me give you an example. Let's think about the time that stress is applied to a material and the effect that that can have. This is silicone putty or silly putty. It behaves in interesting ways to the same amount of stress. Let me show you what I mean. Let's start by applying a very rapid stress to this. If we look at how this material has behaved, you can see we've got quite a sharp edge there where the material is actually broken. You can see it's effectively snapped. We'll look at the type of deformation shortly, but we can be thinking about what does that mean in terms of rocks? What's the geological significance of that? Let me show you a similar deformation now, similar amount of stress, but this time I'm going to apply the stress slowly. So again, I'm applying a tensional stress. You can see this time though, the silicone putty is behaving very, very differently. It's still deforming, but the deformation is very, very different. So that's about the same amount of stress as before, pulled it apart the same amount. How has it behaved this time? Again, what's the geological implications of that? What would this tell us perhaps about if rock was subject to stress over a long period of time compared to a short period of time? Okay. Temperature also has a significant effect as well. And in particular, how materials might respond to that stress. Let me show you an example of three different materials. Let's have a look at three different materials and how each of these materials will show different types of strain when subjected to stress. Like in your booklet, we have an elastic band. I've got some plasticine. And seeing as it's just after Christmas, I've got a mince pie rather than a biscuit. Okay, let's start with the elastic band. Now, if I apply a stress to this elastic band, it will deform. However, if I release that stress, what happens to the strain on the elastic band? Can you describe what's actually happened there? So I apply a stress, I release that stress, what's actually happened? This is a type of deformation, type of strain that we describe as being elastic. What do you think are the key features of elastic strain? Let's have a look at some plasticine. Again, I'm going to apply a stress to this. And then I'm going to release the stress. What's happened to the plasticine? How is it deformed? What happened to that deformation when I released the stress that's applied? Do we see a permanent deformation in this material? Now, this type of deformation is called plastic or ductile deformation. How do you think it might be represented in rocks? Do we see rocks that behave in this way? Can we think about why that might be? Our last material is a mince pie with short crust pastry, which is my own personal favourite. Although we could use a biscuit, which would show us the same thing. Let me apply a stress to the mince pie. How has the mince pie responded to that stress? What's happened to the pastry? Is that strain, that deformation, permanent? How is it different from what we saw with the plasticine? How is it different from what we saw with the elastic band? This is a type of deformation we describe as brittle deformation. How do you think this might relate to rocks? What might we see in rocks that would be representative of this type of deformation, of this type of strain? Do you think this takes more stress to deform a rock like this than it does to deform a rock in a plastic or ductile way? What do you think the role of temperature might be in this type of deformation? What might the role of different types of rock be in this deformation? Have a think about these questions and have a go at the questions on page 3. Okay then. So we should have seen that our elastic band stretched but then returned to its normal shape. This creates what we call elastic deformation. It's not very common in geology, but we do see what we call elastic rebound when stress is building up for an earthquake. The plasticine, which showed a permanent deformation, so when stress was released it stayed deformed, creates plastic or ductile deformation. The geological equivalent of that is what we call a fold, where rocks get bent. And finally, the mince pie, or the biscuit, broke. It displayed what we call brittle deformation, and the geological equivalent of this is a break in the rock we call a fault. We need to look at what these different geological structures are as we make our way through this topic. The type of material, though, also has an effect, and geologists describe this as competence. A competent rock, like the limestone in the photograph here, is one that resists a change in its shape. I feel like it's quite a strong rock. An incompetent rock, like a shale, deforms easily. Rocks like limestone, well-cemented sandstone tend to be competent. Rocks like shale, mudstone, clays tend to be quite incompetent. Let me show you two examples. We've got two lots of folded rocks here, A and B. One of these is quite competent, the other is incompetent. Which one do you think it is? Rock B is competent. If you look at those rocks have been folded, but if you look, the thickness of those beds stays pretty much the same all the way through. It's resisted a change in shape. If you look at rock A, on the other hand, you'll see the thickness of those beds changes a lot. The rock has almost flowed under the stress. So A would be incompetent. So, as I go off to enjoy the mince pie, remember that there are lots of different factors that have an influence on the deformation of rocks. Next lesson, I want to dig into that in a little more detail, but that's for another time. I'll see you then.